So if I look at Hooke's law, this is for physics 151. If I look at Hooke's law, that tells me that the force is equal to negative k delta x. So this is the force. This is known as the spring constant. It also an elastic constant. And this is the displacement. Now, normally when you're dealing with displacement, displacement is from the starting point. We have displacement slightly different here. The slight difference is that this is an indication of position with respect to equilibrium. So if I have a spring here that's just kind of hanging down, this is an equilibrium position. It's just sitting there, not accelerating one way or the other. If I pull it down, then the spring exerts a force back up. The spring is trying to get back to equilibrium. And so if I pull it down to here, this is my delta x. Now, often it's just really convenient to talk about it in terms of just x, that if we make this equal to 0, then, again, going through the math here, we have x final minus x initial equals x final minus 0, if this is my x initial, which is equal to x final. All right, so if I take this, if I attach a mass to this, and so we'll have the mass at the end of, we'll make this ideal. So, which means this is massless. It also means that it's not going to interfere with itself. So if you have a slinky, I can stretch a slinky out, but there's only so far I can compress it. In an ideal one, I can compress it. It will not interfere with itself. So all the mass is concentrated right here. I have its equilibrium position. I pull it down and I let go. Well, if I look at the forces acting on it, so when the mass is here, I look at the forces, I have a force acting up. That's what the minus sign is telling us, is that since the displacement is down, the force is in the opposite direction, which is up. If I push the mass up, then the force will be in the opposite direction, which is down. The force is always towards equilibrium. So I take my mass, I take my spring here, and I attach a mass to it. So this is my equilibrium position, so this would be x equals 0. We'll make to the right positive. I take my mass and I stretch it out to here. And then I let go. So if we do a force diagram of the mass at that point, I have weight acting down, I have normal force acting up, I have kx acting towards the center. That's the positive direction in that way. So if I plug into F equals ma, yes, normal force minus weight equals 0. That's irrelevant to this problem. But I have negative kx is equal to mass times acceleration. Which means that if I add kx to both sides, I have 0 equals kx plus ma. So whatever my function is for x and whatever my function is for a, I know that this is the slope of that graph. Therefore, I need some function that when I take the slope of the slope, I end up with what kind of looks like what I started with. And with that is part of another video, and there is indeed something that does that. So I have 0 is equal to kx plus ma. So if x is equal to some amplitude times the cosine of omega t, then I know that velocity is equal to negative a omega sine omega t, and my acceleration is negative a omega squared cosine omega t. If I plug into here, I end up with 0 is equal to k times a, this is my x here, cosine omega t, plus mass times negative a omega squared cosine omega t. I now look at my factors and what can I cancel out? Well, I've got a couple things that will cancel out here. I can divide everything by a, and a's would cancel out. I can divide everything by cosine omega t, and cosine omega t cancels out. And what I'm left with is 0 equals k plus m omega squared, negative m omega squared. Bringing this over here, I have m omega squared equals k, omega squared equals k over m, omega equals square root of k over m. So if something is in simple harmonic motion, again, let's think about what that means. If something is in simple harmonic motion, that means it's oscillating back and forth. It obeys that Hooke's law and can be expressed by the position, velocity, and acceleration can be expressed by this function right here. Or it could also be expressed by sine. We can make it slightly more generic. We have a cosine omega t plus phi. This would be the much more generic one. This right here is known as the phase shift. So a cosine curve looks like that. But if I'm dealing with real life and something oscillating back and forth, it's not necessarily going to start at the peak. It might start at this point right here. So if that is time is equal to 0, then we need to, it's basically the same cosine, we just have shifted it left or right. And so that's what the phase shift does, is it allows for things not to start perfectly at the peak, or if it starts in the middle, sine might make more sense. But this is just shifts the graph to left and right. This number right here will stretch it out or shrink it, we'll shrink it or stretch it out. This number right here will expand it that way. And we can add one more if we needed to. We can always add a sort of an x sub naught, which can shift it up or down. We're not going to worry about that for this. If we were doing labs with this, it might make a difference, but we will assume equals 0. Assume equals 0. Phase shifts might come into play or might not. For the most part, we're going to ignore that in 151, but recognize the graph can shift left or right.